Assessing timber and concrete moisture. Assessing moisture in timber and concrete moisture is an essential part of laying most timber floors. However, many people who should have moisture meters do not, and some that do don't use them correctly. So, it's important that we cover these three aspects: why moisture assessment is important, assessing moisture in timber, and assessing moisture in concrete. Knowing the moisture content allows us to make predictions on what may happen with or to timber flooring. If we simply look at a piece of timber or a concrete slab, we cannot determine with any degree of accuracy the moisture content. A piece of timber with a 20% moisture content will appear no different to a piece of timber with a 10% moisture content. Timber flooring is moisture tested to ensure it has been supplied within the specified moisture content range, to assess whether it is likely to swell or shrink after installation, and assess if the floor has been moisture affected. With concrete subfloors, they are generally tested to assess if slab moisture is likely to affect the timber flooring laid over it. There are three ways of assessing the moisture content of timber. Each has its constraints or limitations. The oven-dry method is the only accurate method of determining moisture content, but for a floor that has been laid, it requires samples to be removed from the floor. Resistance moisture meters provide a reasonably accurate assessment of the moisture content, but because they need to have pins inserted into the floor, they also create some damage and have limited use in completed floors. The third method is the capacitance moisture meter. This is a little less accurate than the resistance meter, but has the advantage over other methods in that it is non-destructive and can take many readings quickly. The oven dry test method is the most accurate. It determines the moisture content by measuring the loss of water from the timber sample by drying it. Using a laboratory oven and an accurate set of scales, the weight of the dry timber with no water and the weight of the water that was in the timber can be determined, and from this, the moisture content. Things to note about this method: an oven temperature of 103 degrees Celsius plus or minus 2 degrees Celsius is used. Balance accuracy needs to be 0.01 grams for samples up to 50 grams. Test pieces, 15 millimeters to 30 millimeters long, are used, and it is necessary to ensure samples are in the oven long enough to fully dry. This method is needed with plywood and particle board and can be used with engineered flooring and bamboo. And it is very accurate, plus or minus 0.2%. So, the percentage moisture content is the weight of water divided by the weight of dry wood, and the result is multiplied by 100. The weight of water is the weight of the initial sample, less the weight of that sample with all water removed. That is, its oven dry weight. In the example on the left, if we subtract the oven dry weight of 29.49 grams from the initial weight of 32.63 grams, being the wood plus the water in it, and then divide the result by the oven dry weight and multiply by 100, we get 10.65% moisture content. To also help conceptualize the meaning of moisture content, 12% moisture content can be thought of as 0.12 kilograms of water for every 1 kilogram of dry wood. The photos show oven dry moisture content testing of solid timber and some engineered flooring. Solid timber can be segmented into thirds from top to bottom, and each tested to assess moisture differences between the top and bottom of the boards. Similarly, with engineered flooring, it can be segmented into lamella, core and base layer, and the moisture contents of each determined if desired. This approach allows moisture imbalances to be assessed. Resistance moisture meters require pins to be driven into the timber. The meter measures the electrical resistance between the pins. Low resistance means high moisture content, and conversely, high resistance means low moisture content. So, moisture content is related to the electrical conductivity of wood. When using these meters, remember, meter manufacturer instructions need to be followed. Some meters have built-in species corrections, but be very careful of using these, as they can be wrong. Some meters have built-in temperature correction. This is a good feature. The meter reading should be taken straight away, at which time the reading is highest before it lessens a little. Avoid using in sapwood. It's often the lighter coloured wood in a board which could have treatment chemicals that can interfere with a reading. And these meters are not reliable in particle board or plywood or bamboo. These meters measure the electrical resistance of the wood. Each timber species has different resistance characteristics, so corrections need to be applied. It's also necessary to measure and correct for wood temperature variations before applying species correction. Here's an example. Readings are being taken in both the top and bottom of a cupped 130 by 19 mm black butt floorboard. See the top table showing wood temperature corrections. A digital thermometer shown in the top right image can measure wood temperature. Note that it is wood temperature, not air temperature, that we are looking for. At a wood temperature of 29 degrees Celsius, a reading of 11% in the top of the board corrects for temperature to 10%, and a reading of 16% in the bottom of the board corrects for temperature to 14%. Now we correct for species from the second table. Blackbutt is a +1 species correction across the full range. The estimated moisture contents are therefore 10% plus 1% equals 11% for the top face, and 14% plus 1% equals 15% for the bottom face. The previous slide effectively illustrates moisture gradient testing. With a moisture gradient test, the pins are driven from top to bottom of the board and readings taken in the upper, middle and lower part of the board. High moisture in the lower part of a board is a cause of greater swelling to the bottom of the board, which results in cupping. Using a resistance meter on strand woven bamboo can give variable readings, and it is not considered reliable. For laminate flooring, the meter is also not reliable due to the fiberboard core. However, indicative readings can be useful to assess if a floor is water affected or not. So in bamboo and laminate flooring, resistance meter readings are used only for comparative purposes. However, some engineered flooring can be assessed by taking a reading in the face lamella either from a fresh end cut or in the surface without penetrating the glue lines. Glue lines give false readings. For example, this engineered flooring is of a similar moisture content through the board, yet when the moisture meter passes through the glue line, the reading increases by 4%. Capacitance moisture meters do not damage the surface of flooring. These meters measure a different electrical property to resistance meters, but one which again varies with the amount of moisture in the timber. When using these meters, remember, the reading is biased closer to the plates. Firm contact with the wood is needed. They cannot read moisture gradients. Timber thickness affects readings. Cupping affects readings. Species mixes will give variable results. They can be unreliable with brush box and treated material. With timber floors, they are used for survey work rather than to provide a close estimate of moisture content, and manufacturers may use these meters for quality control work when calibrated with oven dry testing. Note that meter electronics differ between manufacturers, so different meters have different characteristics. So, it is important to know your meter. These meters measure the dielectric constant that rises with both increasing wood density and increasing moisture content. So, what does this mean? Look at the graphs on the right side of the slide. If we have hoop pine at 20% moisture content, then it has a dielectric constant of 4. If we have blackbutt at 8% moisture content, it also has a dielectric constant of 4. However, hoop pine is a much lower density than blackbutt. Therefore, meters must be set to approximate density or specific gravity of the timber being tested to get a useful moisture content reading. The top left photo shows 3 capacitance moisture meters, and you may be wondering why they are not called dielectric moisture meters. There is also a photo of a blue electrical capacitor, and you will note that between 2 electrode plates, there is a dielectric ceramic disc. Now to the bottom left-hand diagram. The meter has 2 electrode plates, and the timber becomes the dielectric. So the meter is a capacitance meter. We've mentioned both density and specific gravity. So let's discuss the difference, because some meters read wood density and others specific gravity. Density is the weight of the wood divided by its volume. Examples are the density of water is 1,000 kilograms per cubic metre equals 1 gram per cubic centimetre. The density of spotted gum is 1,100 kilograms per cubic metre equals 1.1 grams per cubic centimetre. And the density of hoop pine is 500 kilograms per cubic metre equals 0.5 grams per cubic centimetre. Specific gravity is a ratio of the density of wood to the density of water, or simply one divided by the other. Hence, the specific gravity of water is 1.0, the specific gravity of spotted gum is 1.1, and the specific gravity of hoop pine is 0.5. When wood has a specific gravity greater than 1, timber sinks as the timber is heavier than water. But up to 1.0, it will float at different heights. As shown, spotted gum sinks, as its density is 1,100 kilograms per cubic metre. However, hoop pine floats at about the halfway level, as its density is 500 kilograms per cubic metre. It is important to know and understand your metre. Here are 3 examples. The Wagner MMI 1100. Settings are on specific gravity at 12% moisture content up to 1.0. Scanning depth 25 millimetres, and there is little information on Australian species. The Merlin PM1E. Settings are on density up to 1.1 grams per cubic centimetre or 1100 kilograms per cubic metre, and scanning depth, by experiment, about 12 millimetres. Due to density differences between boards, readings fluctuate a little from board to board, and therefore, with the metre on the right, the manufacturer has simply provided 5 classes from exceptionally light through to exceptionally heavy. This is a reasonable approach with this type of metre. This slide shows 3 methods of assessing the moisture in a concrete slab. The first is an impedance meter that assesses moisture in the upper 20 millimetres or so of the slab. The second is an in-slab relative humidity measurement that assesses the humidity of a pocket of air, usually about 40 millimetres below the slab surface. The third photo uses an insulated polystyrene chamber above the slab where the relative humidity of moisture from the slab can be measured. Of the 3 different methods of assessing slab moisture, the first 2 are the most common in Australia. Many concrete meters are impedance meters, and they work similarly to timber capacitance meters with 2 electrode plates in the base of the meter and an electric field that passes through the concrete between the electrodes. The Tramex, which is popular in our industry, is characterised by spring-loaded electrodes on the base of the meter to compensate for concrete unevenness. These meters use low-frequency alternating current, AC, to create an electric field between the plates. The very low AC flowing through the field is inversely proportional to the impedance that varies with concrete moisture. The impedance is measured and converted into a reading of the concrete moisture content. Meters are often used to assess risk where the information in the table is used to guide the assessment. The table has slab age, moisture content and risk as the parameters for assessment. From the table, you'll see a very young slab would be considered a very high risk. During the first 3 to 6 months, the slab will be drying, and moisture meter readings should show this with readings of say 3 to 4%. Slabs a few years old often have moisture contents below 3% and risks are low, but older slabs with higher readings above 3.5% are of higher risk as the readings should be lower for this age of slab. This can help the installer to decide which slab moisture protection option to use. The graph shows the readings from an impedance meter on a new slab over an 18-week period. Within the first 20 days, readings go to 5%. With some rain before the house is fully closed in, readings temporarily rise. After this, the house is closed in and there is a steady decrease in slab moisture content to below 4% after about 4 months. In-slab relative humidity is increasingly relied on throughout the world, and many flooring contractors also use this method. It is not as convenient to measure, but tells you more about what is happening in the concrete and the level of protection from slab moisture that is required. To comply with American standard ASTM F2170-02, the following is necessary. Regular checking of the calibration of the measuring instrument. The slab is to be at service temperature and service relative humidity for at least 48 hours. 3 test holes for the first 100 square metres and at least 1 additional test for each additional 100 square metres. Test holes need to acclimatise. Probe needs to be left in the hole until stable, and they must record results. Measuring above-slab relative humidity is not as convenient as using an impedance meter and not often used in Australia with timber flooring. However, in places such as New Zealand, it is frequently used. It assesses moisture migration from the slab or moisture barrier surface. It measures humidity build-up to 70% would often be considered acceptable. It is used more so in colder, wet climates where slabs are slow to dry, and care is needed to ensure a good seal to the slab and that is not accidentally dislodged during the testing period. 3 methods have been outlined, and it is important to consider the differences as each assesses slab moisture in a different way, and each is not directly comparable to another. As a concrete slab dries, the relative humidity in the slab reduces toward the upper exposed surface. It dries from the exposed surface, and the drying depends on the relative humidity of the air above the slab. The graph with the light blue line may represent the relative humidity profile after 6 months and indicates about 50% RH at the surface and near 100% at the bottom of the slab. Above-slab RH measures the moisture vapour coming from the slab and through any moisture barrier. This indicates whether there is enough moisture coming out of the slab to affect a floor. Impedance moisture meters assess the moisture content in the top 20 millimetres or so of the slab. They are very useful for survey work, but have limitations. These two methods do not allow for the fact that once a slab is covered by a floor, moisture from deeper in the slab will rise to the slab surface. As indicated, in-slab relative humidity is becoming the recognised method of assessment. Measurements are taken at 40% of slab depth, and at this depth, it provides a prediction of future moisture conditions at the slab surface after a floor has been laid. It is the ability of this method to predict future moisture levels near the slab surface that makes it attractive to use. However, testing to the standard would not necessarily identify slab edge moisture effects. For optimum confidence, a range of options should be available. That covers the necessary aspects for assessing moisture in both timber and concrete. Key points to consider are: 1. Moisture testing in timber is not only important to tell if the timber has been affected by moisture or dried properly, but it also helps predict and minimise the effects of movement, shrinkage or swelling, after a floor is installed. 2. There are 3 methods to assess timber moisture: the capacitance meter, least accurate but most convenient; a resistance meter, a little more accurate but it damages the board surface; and oven testing, the accurate method, but it needs samples to be removed from the floor. 3. Moisture assessment in concrete is done to ensure slab moisture is not going to affect a timber floor, and this can relate to isolated areas in the slab, for example, slab edge dampness, or moisture throughout a slab. An old slab is not necessarily a dry slab. And 4. Measurement uses impedance meters and both above and in-slab relative humidity. Each method assesses a different aspect of slab moisture.